second speaker today are from Siemens, Kaushal, Shah and Sulabh-Kumar. They've taken a presentation from DVCon 2021 in Europe, detection of glitch-prone clock and reset propagation with automated formal analysis. Okay, so Sulabh oversees the development of Questa CDC product line at Siemens EDA and has over 14 years of experience in developing EDA software for design and verification, and holds a master's degree in VLSI design from IIT in Khare, and Kaushal was making today's presentation as a senior member of the R&D with Questa static and functional verification team. He postgraduated in microelectronic and VLSI design from IIT Khare as well. Over to you, Mr. Kaushal.
Okay. Thanks, Mike.
Thank you.
Okay. So hello, everyone. So in this presentation, I will be discussing on the detection of glitch on the clock and reset paths with the automated formula analysis. So the agenda would be simple. We will first introduce why we require a necessary step after the RTL verification for glitch checking, and then we can see what are the reasons that are there for the introduction of glitches in the design at the netlist level. We will then again go through some of the existing methodologies that are there for the detection of glitch, and then the proposed solution that we are proposing in terms of why it's better in terms of methodology and the performance, and then the summary part. So in this slide, as we go down the timeline in the development cycle, the pressure keeps on mounting even after the RTL CDC sign off. So we do the CDC verification, which is a critical step in the design verification cycle, mostly at the RTL stage, that is the register transfer level. So this helps us to ensure steady signal pass across the clock domain's boundary without being missed or causing any metastability. But during the synthesis stage, when the design is transformed from RTL to gate level, some new issues like glitches can be introduced that may eventually lead to chip failures. So even after the CDC verification closure at the RTL stage, it is important to perform the CDC verification on a gate level design to detect and address new issues. So in this presentation, we will mainly focus on the glitch issue that is being introduced. Okay, so let's first understand what are the different glitches and how we can narrow them down in the combination logic. The first one is the static zero glitch. So the static zero glitch is mainly formed by the convergence of two paths that are, this is the one path and this is the second path, that is X and not of X. So whenever we see a logic of X, not of X combining in our, you can say combination logic in the design, we can say that the static zero glitch can be introduced. Similarly, static one glitch can be introduced by the convergence of two paths. It's the signal and the inversion of signal at the OR gate, which leads to the static one glitch. Again, X OR with not of X. So these are the two static glitches, and the third part is the dynamic glitch. So the dynamic glitch is the advanced part of the static glitch where the data changes more than once. So here you see the data should have gone from 0 to 1, but it changes from 0 to 1 and then again goes from 1 to 0 and finally to the 1 value. So here it's a combination of two static glitches. So here you see this is one of the static zero glitch, and then again the signal is combining here to form a dynamic glitch. So we can narrow down the combination logic for dynamic glitch as this or this one. Okay. So glitches are mainly the unwanted spikes that we do not want in a design, but it can propagate through the combination logic. At times, signals display the incorrect intermediate value. So here we would have always known that X and not of X combined would have been 0, but it shows the intermediate value of 1. Okay, so in this slide, I will show you how you can say clean RTL logic can introduce some CDC bugs or may introduce some glitchy logic. So here the RTL return is for a demux crossing, and the changes introduced in the netlist during the synthesis stage, such as the timing optimization of synchronization logic and the insertion of DFT logic, or maybe the low power circuitry, may cause incorrect behavior. For example, new clock domain crossings can be introduced due to insertion of low power logic. So it may happen that due to new power domains are created and there are new CDC crossings. Similarly, due to scan logic insertion, a clock tree can be impacted because we may have missed the constraints to provide for the proper modes of the design, in which modes we run to design. So the questions can be raised like, if the RTL is correct, if we are mapping my RTL logic to some logical equivalence to the generic technology or some specific technology, depending on the constraints that are there, maybe the area constraint, timing, such optimizations. So does my synthesis introduce new issues or not? Am I clear if I just do the RTL sign off? So no, so that's there. And let's see a clean, you can say, schematic of the RTL. This is the demux crossing, which can be considered safe at the RTL level. So there is no, you can say, possibility of metastability in this RTL. But during synthesis, this logic can be transformed. The synthesis may optimize the logic in such a way that may introduce a glitch. So here, this mux and the AND gate are now combined, and you can say synthesis does some optimization, which can be due to the area or timings, and then this logic is created. So here is, you can see, if my tx1 is kept at value 1 and my this you can say select synchronizer is kept at value again 0. So you see there's a static 1 glitch being formed. So this x plus not of x combining as this output of the OR gate. So we see that during synthesis, the safe RTL can create some issues that can be, you can say, some new CDC parts or the glitch. So here we are seeing a live example of why a synthesis introduced is a glitch. Okay, so this is clear, right? This is on the CDC part. The same can happen on the clock or reset parts. So in the next couple of slides, I will show you the different implementation of same mux logic at the RTL, which can introduce glitch on the gate level netlist. So here we have just transformed simple mux implementation to its gate level implementation. Here, if A and B are kept at value 1, we can see that again cell and not a cell can combine to create a glitchy logic on this reset path. And this can cause some unwanted resets, or this may again cause, you can say, the entire design to go into the reset state, or may introduce the metastability whenever there is, when you can say the register is going out of the reset state and the clock arrives at the same time. So this may create some metastability issues downstream. Okay, and this problem is happening on both the synchronous paths and asynchronous paths. Okay, the next is on the same glitch mux logic is transformed to 3 AND gates. Here, if the value of A is 0, A is 1, and select as 0, we can see B will form a glitchy logic. So the source of introduction of glitch is B. So it depends on like what are the constraints for the synthesis, how synthesis performs the optimization on the combinational logic, and what's there at the gate level. So it's very necessary to perform a gate level CDC verification, glitch verification to catch these issues. Okay. Now in this slide, we will go through like what are the existing methodologies that are there to detect glitches. The first one is the simulation, gate level simulation, which is very exhausting, time consuming. For each of the clock or reset paths with the combinational logic, the receiver value can be sampled in the simulation. But the sample values can then be used to identify the presence of the glitch logic in the path. But due to the asynchronous nature of the signal paths, many simulators have difficulty sampling the signal paths at the times when the glitches are actually present. So even if the simulator catches a glitch, a waveform is present, it is very difficult to manually identify the source of the glitch path. So we are uncertain, like what's the source, and do we need to add some, you can say, glitch cover logic or not? Okay, the second methodology that is there is to write assertions. Some verification engineers have elected to write assertions to check if the simulators are sampling the signal paths at the correct time. But the results of sampling checks are often not accurately captured by the simulators. Assertions also have some semantic limitations when it comes to the asynchronous clock and resets, and it may happen that all simulators does not handle the assertions, this kind of assertions that are there to capture the glitch. So writing assertions and validating it itself becomes a mammoth task. And the third one is on the static checks. So what happens is some employ methodology where we detect every clock or reset path with combinational logic to manually inspect them whether there is any glitch or not. So this is a very, you can say, time consuming and difficult task to detect whether the synthesis introduces some new logic, or you can say breaks the combinational logic, and it may happen to have a glitch or not. So all these three are, you can say, are noisy. It sometimes it may have it may consume time. Like for the example of gate level simulation, it's difficult to write the assertions. The static checks are not valuable because we need to spend a huge amount of time, and as the development cycle is near, we are crunched for the time. We cannot spend a lot of amount of time during the gate level glitch analysis. Okay, so so what we introduce is the 5-level methodology to verify glitch on the gate level designs. Okay, the first step is of the design setup. We get the gate level design files and the initial constraints, like the top level clocks, reset, design modes, and the cost schedules.
Just as a reminder, you've got 3 minutes left. Okay.
Okay. So next one is to detect the paths, identification of the clock and resets, and marking all the registers in the design with their corresponding clock and reset domains. So we use the same RTL constraints and use the transformation engine to transform this RTL constraint to the gate level constraints. The waivers at the RTL, again, using the same transformation engine, we develop the waivers at the gate level constraints. Now we detect the, you can say, combinational logic. We do the expression-based analysis, which identifies the combinational logic that may contain the glitch. Now the next step is to perform the gate level, you can say, formal analysis on those combinational logic to identify whether the glitch actually propagates to the receiving logic or not. So the glitch list is further pruned to identify the scenarios under which the glitch really propagates. So we, for this, we utilize the formal engines to verify the glitch propagation conditions and conclusively give counterexamples for that. Okay, and the next step is to debug it on a schematic so that we can show that where is the converge point where the glitch is actually introduced and where it reaches. Okay, so this was employed on 2 of the SOCs. One was having 10 million gates, then the second was 2 million gates. So these are the results from the clock and reset glitch analysis for them. The first one is a clock glitch results. So you can see for the 10 million gate design, the number of glitches signals that are shown are only 68. So there's a huge reduction in the number of noise. This is one of the schematic paths for the glitch. Similarly, for the glitch results, we see very less number of glitch signals. So the user doesn't need to spend a lot of amount of time to identify like what are the glitches as compared to the other methodologies. Okay, so this is the scheme reporting for the reset glitch information. So we report the glitch signals. We are giving the converging point and the receiving node. So along with that, we have the glitch propagation conditions, like what are the values for which the glitch signal A will reach to the value, the receiving node. Along with that, we are giving the schematic information along with the propagation conditions marked on them. So this helps the user to understand like the signal S will cause a glitch and it will go to the reset pin for these particular values. So to summarize, the proposed methodology intelligently identifies the unique paths which may be glitch prone and perform an automatic formal based glitch analysis to improve the quality of results. This in result ensures that the glitches are reported with minimum noise and gives deeper gates such as the schematic and the propagation conditions to identify the glitch source and the converging point. The generation of counterexamples under which the glitches would propagate makes it obvious that the reported issues are genuine and pose serious threats to the next SOC.
Okay.
Advanced.
Okay.
Okay.
Thank
I
you.
believe that's, yeah.
Brilliant. Okay, thank you very much. Fortunately, we don't have time for any questions, but thank you for the presentation, and we'll provide the slides afterwards. Okay, thank you, Kaushal.